and as well as the half-life. Since it's going to be a long lesson, I'm just gonna teach about nuclear equation right now and half-life. The next meeting will be the rest of the radiation, like uses and whatnot, and even the nuclear fission and fusion. So let's review first what we've learned last week. So I gave you here a mass number. So nuclear symbol I-131-53. So again, let's review what goes on top, number, and this number here, 53, and what is I. Okay, this is a nuclear symbol, right? Okay, so make sure you know how to identify. Right, so this is the mass number 131, this is the atomic number 53, and the symbol of the elements I. Okay, so I'll make sure you know that one. Again, let's review. Gallium-68 is used for detection of pancreatic cancer. So how many protons are in gallium-68? How many neutrons are in gallium-68? What is the nuclear symbol of gallium-68? Okay, so pause this answer and I'll reveal the answers after. Okay, so if you've looked into your periodic table, of course you need your periodic table here. How many protons are in gallium-68? So answer is you need to look for gallium in your periodic table. Gallium has the symbol Ga, so the atomic number is 31. Therefore, number of protons is also 31. How many neutrons are in gallium-68? So I'm going to subtract 68 minus 31 because 68 is the mass number and 31 is the number of protons. So 68 minus 31. So that would be 37. Okay. Now what is the nuclear symbol of gallium-68? So the nuclear symbol of gallium-68, I'm just going to say it. It's capital G lowercase a, and the number on top would be 68. Number at the bottom would be 31. Okay. So just reviewing what you've learned because you'll be applying that in the next lesson. Okay. So let's review again. We've learned these particles last time. What is the symbol of alpha particle? What is the mass number of a beta particle and its charge? What is the symbol of positron? What is the mass number and charge of gamma ray? Okay, pause and then answer. Okay, so the symbol of alpha particle, you could use the symbol alpha or you can use He. Okay, and then if you're looking for the nuclear symbol, that would be He, and then the top would be 4 and the bottom number would be 2. Number 2 here, what's the mass number of beta particle in this charge? The mass number is 0 and the charge of a beta particle is -1. Okay, symbol of positron, again, it's kind of like that B, but different style. Or you can just write letter E. So the symbol, if you look at the nuclear symbol, would be that particular character, like the E or the B character, beta. The top would be 0, and the bottom would be +1. What is the mass number and charge of gamma ray? The mass number and charge of gamma ray is 0 and 0. All right, so let's go to nuclear equations. So in nuclear equations, you will find how the particles decay, like alpha, beta, gamma, so on and so forth. So first one, in radioactive decay, a nucleus spontaneously emits radiation. And a nuclear equation is written for the radioactive nucleus, the new nucleus, and the radiation emitted. So you're going to find out later in the samples. So I showed you this last time. You have alpha decay, the radiation symbol or nuclear symbol, mass in or change in mass number, atomic number, and change in neutron number. And we have the beta, positron, and gamma. Okay. So this one, in a balanced nuclear equation, the sum of the atomic numbers for the nucleus of the reactant particle must be equal. So I've taught you this um, last time, right? In a balanced nuclear equation. Um, so you have, for example, the mass number is 238 on this side before the arrow. After the arrow, the mass number, you have to add 234 plus 4 to get 238. That means the mass numbers are balanced. So the bottom is 92 here. 90 plus 2 will give you a 92. So they have to be balanced. You just need to add the ones that needed to be added because you can find that plus sign. So how do we complete a nuclear equation? So you can copy this part and you can study it on your own, but just pause it, okay, when you watch this video. So let's start with alpha decay. So for the alpha decay, a radioactive nucleus emits an alpha particle to form a new nucleus that has a mass number 4, and then of course the atomic number is 2. Okay, so let's try. Example, how do we write the equation for alpha decay of radon 222, and then of course an 86 atomic number? So write the complete nuclear equation. So I'm going to write that down. I'm going to write this. I just copied that from the given. And I'm going to put an arrow and then a question mark because I don't know what element was formed here if there's an alpha decay. So decay is at the what's on the right side. So you have, because it's alpha, so it's 4 2He. So now how do you determine this missing number? First, let's do the mass number. So you have 222 here and you have 4 here. So that means you subtract 222 minus 4 to get this 218, because when you add 218 plus 4, it becomes 222. So they have to match, right? Both sides. So take note of that number. The new mass number would be 218. Now, how do you determine the missing atomic number? So if you go back, atomic number is 86. So you just stamp, and then there's this question mark, and then you plus the atomic number on the helium, which is alpha, is 2. So 86 minus 2 becomes 84. So you look in your periodic table, what is 84? It's polonium, okay? And then you just write and complete the nuclear equation. Just copy whatever I had earlier, and I just added the new element form as polonium, 218, okay? So that's pretty much it for alpha decay. For beta, it occurs when an electron is emitted from the nucleus and a neutron in the nucleus breaks down. So let's see. Example here is write the equation for the beta decay of potassium 42. So you have to just write 42 on top, 19 at the bottom is the atomic number. It's not given in a problem, but it's in your periodic table, okay? Potassium. Again, you're looking for that question right here. And then you have the beta here. And then you determine the mass number 42, and because this is 0 here, just gonna be minus 0, so it's the same number. If it's beta, because the mass number is 0, it's gonna be the same mass number. The only thing that will change is the atomic number. So on this side you have 19, I mean, and on this side you have -1. So you have to move this -1 to the right, to the left side, I mean, and plus 19 plus 1 becomes 20. And then that would be the new atomic number, because you just want to make sure that both sides have, I'll show you the answer. Both sides would have the same number, okay? Same number altogether, like a total. Okay, symbol of the element 20 is Ca if you look in your periodic table. So you have here 42, right? So this side, after the arrow is 42 plus 0 is 42. It says 19. So what number do I need to put here that should give me this same number? So 20 minus 1 is 19. Okay. Now, write the nuclear equation, learning chat. Okay, write the nuclear equation for the beta factory of xenon 133. Again, write the incomplete nuclear equation, this mass number, atomic number Xe. Okay, what is this here? And then, of course, this because it's beta, it's -1. So, again, I repeat, the mass numbers are already have been given to you. So, we're going to write 133 minus 0. That's this one here, 0. Then look at 133. So for the other one, 54 plus 1 would give you 55, because if you put a 55 here, it's -1 becomes 54. Please, I hope that makes sense. The symbol of the element 55 CS, how do you know? You look in your periodic table. So this is the outcome of the nuclear equation. So sorry, the spacing is a little bit different. Okay, so positron is the same thing, but the atomic number decreases by 1. Okay, so just it's the same thing like this, but this one would be a plus. So of course this one will change. Okay. Here's an example. Write the nuclear equation for the positron emission by rubidium-82. So rubidium-82, 37, that's the atomic number of rubidium. And then the question mark here, and of course a plus here. So 82, same. 37 minus 1 is 36, because it's a plus positron. 37 has to be, what number is this to make up 237? So this, you already have 1, just need 36, right? Plus 137. I just shortcut it, but this is the explanation. Okay, so the symbol of element 36 is Kr, but there's a new element that's formed. So sorry, the new element that's formed is Kr, okay, from rubidia. Any questions on this one? No. Okay. Gamma radiation. If you see a decay, gamma radiation, it's ending. It's done. I mean, yeah, it's already. You don't need to solve because it's 0. Okay, so just follow the same thing. Copy it. All right. So here, summary of types of radiation. If it's an alpha alpha particle, alpha decay, there's a new element. Okay, and this is the radiation that you will see. If it's a beta, this is the radiation you will see. That's a new element also. Okay, and then it's also it says here what you need to do. So very, very easy. Positron, again, new element, and gamma, stable, same. Okay. So producing radioactive isotopes. Right. Let's not talk about that one, but never mind that one. Let's continue to nuclear radiation. I gave you breakfast anyway. So let's go to half-life. Okay, so this is a picture of a Dead Sea Scroll, and they were able to determine the age using carbon dating, carbon 14. So what is half-life? The half-life of a radioisotope is the time for the radiation to decrease to 1/2 of its original value. So it's, for example, the half-life of, let's say you were exposed to a certain radiation. How long does the radiation last in your body, and what's the half-life? So just, making sure that you're safe. So this is iodine 131. The half-life of iodine 131 would be maybe 10. Okay, and then of course value decreases in half. That's the second half-life. Then that half will divide into 2. That's the second half-life. And that 1/4 will divide into 2. That's 1/8. So it's from 20 to 10 to 5 to 2.5. I think that there are examples here. Okay, so don't worry about that one. Here are the half-lives of naturally occurring elements used in nuclear medicine tend to be short. Okay, so these are the half-lives of the following elements. Okay, how long the radiation will be stopped. Okay, so half-life calculations. In one half-life, 40 milligrams of radioactive isotope decays to 20 milligrams. After two half-lives, 10 milligrams of radioisotope remain. Okay, so from 40 divided by 220 divided by 210. The first half-life is here, the second half-life is here. All right. So again, the half-lives. So how do we solve for half-lives? You can take a picture of this in your notebook and take note of that, to be able to master. So the half-life of iodine 123 is 13 hours. How much of a 64 milligram sample of iodine 23 is left after 26 H? Is it 1, 2, or 3? So state the given needed amount of radioisotopes. So that one, you need, okay. Write a plan to calculate amount of active isotope, half-life, number of half-lives, and so on and so forth. Write the half-life equality, and conversion factors. So one half-life is 13 hours. Sorry, where did they get this? It's from the, yeah, it's from the given in the problem. Set up problem to calculate the amount of active isotopes. Okay, so that's two half-lives. All right, so that's the end of my presentation. There's work for you to do. Please follow.